ME 347, Example 10. Air flows between two sections in a straight pipe of constant area and elevation at a mass flow rate of 2 kilograms per second and a velocity of 46 meters per second at section 1. The temperature and pressure are 300 Kelvin and 7 bar at section 1 and 250 Kelvin and 1.3 bar at section 2 further downstream. Calculate the following between sections 1 and 2. A, the change in specific internal energy. B, the change in specific enthalpy. C, the density ratio. D, the rate of heat addition or loss. And E, the change in specific entropy. For this problem, we will assume steady, uniform flow of air. We will also assume ideal gas behavior for the air with constant specific heats at 300 Kelvin. For Part A, calculate the change in specific internal energy from Section 1 to Section 2. In general, the specific heat at constant volume is equal to the change in internal energy with temperature at constant volume. For an ideal gas, where internal energy is only a function of temperature, and for a constant specific heat at constant volume, this definition can be integrated to get the relationship shown. Using the value for specific heat at constant volume for air at STP and the given temperature change, we get a change in internal energy of minus 35.9 kilojoules per kilogram. Note that because this is a temperature change, we can use either degrees Celsius or Kelvin and get the same result. For Part B, calculate the change in specific enthalpy from Section 1 to Section 2. In general, the specific heat at constant pressure is equal to the change in enthalpy with temperature at constant pressure. For an ideal gas, where enthalpy is also only a function of temperature, and with a constant specific heat at constant pressure, this definition can be integrated to get the relationship shown. Using the value for specific heat at constant pressure for air at STP and the given temperature change, we get a change in enthalpy of minus 50.3 kilojoules per kilogram. Again, note that because this is a temperature change, we can use either degrees Celsius or Kelvin and get the same result. For Part C, calculate the ratio of density for Section 1 to Section 2. To do this, we apply the ideal gas law to the conditions at each section and divide the equations. Thus, the density ratio is proportional to the pressure ratio and the inverse of the temperature ratio. Substituting in, we get a density ratio for Section 1 to Section 2 of 4.49. Thus, the air is becoming much less dense and expanding significantly. Note that when using the ideal gas law, you must use absolute pressure and absolute units for temperature. Note that if you used gauge pressure or degrees Celsius, you would get a different ratio, which cannot be possible. For Part D, calculate the rate of heat addition or loss for Section 1 to Section 2. Because we want to know an overall heat transfer rate, we will use a finite control volume or integral analysis. We begin by applying conservation of energy to a control volume from Section 1 to Section 2 to solve for the rate of heat transfer at the pipe wall. For steady flow and for a pipe with constant elevation, we can reduce the equation as shown. In order to complete our calculation, we need to solve for the unknown velocity at Section 2. Thus, we apply conservation of mass to our existing control volume to solve for our unknown velocity. For steady flow, the equation reduces to the mass flow rate in must equal the mass flow rate out. Even though the area remains the same for this case, because the density is changing, the velocity changes. For our expanding air, this corresponds to a much higher velocity of 206 meters per second at Section 2. Finally, substituting into our form of conservation of energy derived earlier, our result from Part B for the change in enthalpy and our known and calculated velocities, we get a heat transfer of negative 60.3 kilowatts. Note that the cooling from Section 1 to 2 has resulted in a significant drop in temperature, pressure, and density, while significantly increasing the velocity. Later, when we model compressible flow with heat transfer, which is called Rayleigh flow, we will find surprising changes in our properties with heating or cooling for our coupled nonlinear equations depending on the Mach number. Thus, we are not ready yet to interpret these numbers. Finally, be careful to note the conversion needed to go from meters per second squared for the kinetic energy term to kilojoules per kilogram. For Part E, calculate the change in specific entropy from Section 1 to Section 2. For an ideal gas with constant specific heats, the change in entropy can be calculated using the relationship shown to get 0.3 kilojoules per kilogram degree Kelvin. Note that we must again use absolute pressure and absolute units for temperature for this calculation.